Much of what we've done in math, not just us together, but by referencing all of your past math experience, we could say that much of what you've done so far has relied on using a general rule to figure out specific situations. So you use a rule for adding and subtracting integers. You use a rule for multiplying fractions. And that allows you to do these specific, particular kinds of problems. That's referred to as deduction or deductive reasoning. We have a rule and we apply it to a particular situation. But we can take those two parts of the reasoning process and we can switch them around, where we say, let's use a particular situation to try to come up with a rule. Another way of thinking of this is, if I can knock down a domino, can I knock down the next one? And if that is doable, then that means I can set up an entire pattern of dominoes and knock them all down. So a particular situation where a domino will knock down the next domino allows us to come up with a general rule of how all these dominoes are going to fall down. That's what we call induction or inductive reasoning. So in this particular video, what we want to do is use the idea of induction or inductive reasoning, and we want to try to prove results. So we're going to say, here is this general rule or a pattern, and we want to prove that it would work by trying to examine a very particular situation. But we can't be too particular about it, so here's how it works, thinking of the domino idea. Let's prove that we can knock the first domino down. Then we will jump somewhere into the middle of our domino setup, and we'll assume that some generic domino is going to be knocked down. And let's show that the very next one would fall. Now, if we can do this, the first one would automatically knock down the second one, and the third, and the fourth. And so that means that, by extension, we would be able to prove that all of the dominoes get knocked down. So here's how this is going. Here is a particular rule. We don't know that it works unless we prove it. We can prove this one by induction. So we'll say that our general rule, our general statement, P with a subscript n, is the statement 1 plus 2 plus 3 plus dot, 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 all the way up to plus n, is going to have this formula result. Now we're going to want to show that that would work for the very first situation, and the very first situation is when the index is 1. So we're trying to keep things a little bit more on the mellow side here as much as possible. So the index is 1, first situation. So the first situation here, according to this rule, would seem to be just a single number 1, and using the formula, 1 times 1 plus 1 is 2, 1 times 2 is 2, 2 divided by 2 is 1, 1 is equal to 1. That's true. That's a true statement. 1 is equal to 1. No doubts about that. So that means the first domino can fall down. Now we need to make sure that once a domino falls down, the very next one will fall down as well. So we would need to make an assumption that somewhere in the middle of all of this, we would have a true statement that we'll assume is all hunky-dory. And if that's all hunky-dory, can we show that the very next step, the very next domino, is going to be knocked down? So let's see if we can try to bring enough of this up that we've got room to work our way through. So we're going to assume that a generic step is actually true. That's when we have an index of k, because we're being generic. The very next domino, as it were, would correspond to an index k plus 1. So if we do this adding all the way up through this k plus 1, will we get this formula from all of that work? That's what we need to prove. Now, if we only look at the first part of our left-hand side and stop at the k, that is going to match up with our previous domino, the assumption that up through adding the k, we would get this special formula. And that would leave adding one more piece and seeing how everything would work. Well, here's a cute little thing. Here's a k plus 1, and here's a k plus 1. So we could do a little bit of factoring. Let's pull the k plus 1 out of there. We'd be left with a k over 2 plus 1. Now this doesn't look quite like we want it to from the formula, so let's tinker with that a little bit. In order to add those fractions together, we need a common denominator, so we make the 1 into a 2 over 2. That gives us, hey, those are the pieces that we need. Let's just write them the way that we would have seen them, in the formula. Parentheses k plus 1, parentheses k plus 2, all over top of a 2. So that shows that that next domino would fall down if the one before it had fallen down. Click, click. So generic index k falls down. Click. We've just shown that the very next domino would fall down. Click. Because that happens, we can backtrack that idea all the way to the front. And if it happens from the very first domino falling down, that automatically means that the second one would fall. Once the second one falls, that automatically means the third one falls. And you know how dominoes work. Click it, click it, click. Let's do one of these together so you can try to get a bit more of the feel of how this is working. So let's also look at something that we've not seen before. Let's look at something like this here. Proved by induction that the expression n power of 3 minus 6n squared plus 11n minus 3 is all divisible by 3. Whatever number that is, it's actually divisible by 3. So we are going to say for our general rule, our general statement, P with the subscript n is the statement n power of 3 minus 6n squared plus 11n minus 3 is divisible by 3. Now we can try and see if we can plug in a 0 or a 1 for this. And so if we plug in a 0, 0 squared, or sorry, 0 power of 3 is 0. 0 squared is 0. That means that this whole statement, n power of 3 minus 6n squared plus 11n minus 3 would give us a negative 3. So there's the statement. Negative 3 is nicely divisible by 3. There is no remainder that is left. So this first statement is true. Now we're going to jump somewhere in the middle, and we're going to say that for an index k, we would have the expression k power of 3 minus 6k squared plus 11k minus 3 is divisible by 3. That's the statement, and we're going to assume that that is a true statement. If we look at the very next index, our expression is going to be more complicated. The index is k plus 1, so that means now our expression would be parentheses k plus 1 power of 3 minus 6 parentheses k plus 1 parentheses squared plus 11 parentheses k plus 1 minus 3. And so that whole big deal is, we believe, divisible by 3, but we actually have to justify that this statement is true. So we're going to have to tinker around with this expression. So we're going to use a little bit of our algebra skills to try to putter around with that bad boy, see what we can come up with. So, whoo boy, if we expand parentheses k plus 1 power of 3, we will get k power of 3 plus 3k squared plus 3k plus 1. If we expand the k plus 1 squared, we've got the minus 6 out in front of that. So k squared plus 2k plus 1. Plus, we can actually go ahead and distribute the 11k plus 11, and then the minus 3 at the very end there. Let's go ahead and distribute that negative 6. So k power of 3 plus 3k squared plus 3k plus 1 minus 6k squared minus 12k minus 6 plus 11k plus 11 minus 3. Okay. Now, remember that we have a particular statement that we can automatically assume is true. K power of 3 minus 6k squared plus 11k minus 3 is divisible by 3. So, let's pick out just the pieces. K power of 3 minus 6k squared plus 11k and minus 3. So if we go through and we highlight those, actually, let's literally highlight those. I'll write them in a separate color in just a minute. So there are those 4 terms. k power of 3 minus 6k squared plus 11k minus 3. Now the other stuff that we still have, let's go ahead and write that now, but let's separate it out. So that means we would still have the plus 3k squared plus 3k. We've got a, we've got a plus 1. We've got a minus 12k, a minus 6, and a plus 11. So, still keeping the stuff in green separate, k power of 3 minus 6k squared plus 11k. Let's go ahead and even throw down our note here. K power of 3, that's a little sloppy. K power of 3 minus 6k squared plus 11k minus 3 is divisible by 3. And this is from our assumption. That's from our assumption here, right about the middle of the screen. That's from our assumption. Now it's all the rest of the stuff, and let's simplify that. The 3k squared plus 3k plus 1 minus 12k. Let's go ahead and write that in a separate color so it stands out a little bit better. So simplified version would still have the plus 3k squared. We have two terms with a k that would combine together to give us a minus 9k. And then we have three constant terms, a plus 1, a minus 6, and a plus 11. And when we put all those together, that would give us a plus 6. Well, since the green part is divisible by 3, if the blue part's divisible by 3, then that means that the whole shebang is divisible by 3. So if we make a little separate note here about the blue stuff, 3k squared minus 9k plus 6 is divisible by 3. Well, 3k squared is negative 9k is 6 is. So all of it is 3k squared. Well, no matter what k squared is, because we got that coefficient of 3, that sucker's divisible by 3. No matter what k is, because we got a coefficient of 9, 9's divisible by 3. And 6 is definitely divisible by 3. So if I add something that's divisible by 3 to something else divisible by 3 to something else divisible by 3, then what I get will all still be divisible by 3. Everything's working out here. And if the green parts and the blue parts are all divisible by 3, then when I add them together, that will be also divisible by 3. So I have proven that when the index is the k plus 1, it will be true as long as the original previous domino had fallen down. So that means that overall, that statement that was originally made, n power of 3 minus 6n squared plus 11n minus 3 is divisible by 3. Happy exclamation point. This is the sort of thing that you would want to do based on whatever it is that you were given as a result. Can you knock down the first domino? After you have figured out that you are in fact able to knock that first domino down, we make an assumption about some generic domino in the middle. Using that assumption, can we prove that the next domino would fall down? Once we can do that, that would mean that the entire set of dominoes would be able to fall down, so the entire general result would be true. It's a bit funky and would take a bit of getting used to, but hopefully these examples help you out and put you in a good position to complete the homework and be in fairly good shape.